In this video, we will use OpenCV to control the car to follow a lane. I upgraded Django to version 3.2.9, which is the latest official version for Python 3. The original code uses Django 2.0, which will not be supported soon. I migrated the code to Django 3.2.9, and in the description, you can find the GitHub link. If you would like to keep Django 2.0, you should still be able to use it with the code changes covered in this video. First, we need to do some preparation. We move monitor URL processing to views.py, so all the processing logic will be accessible in views.py. Later, you will see why we need this. In urls.py, we change the code to specify the monitor function in views.py to process monitor requests. In views.py, we add the monitor function, which is basically the same as what we previously put in urls.py. As we know from the previous video, the video camera class uses OpenCV to read frames from the camera and stream it to the monitor URL. In this video, we will modify this class to, first, use OpenCV to process the frame image to detect lane and calculate steering angle. Second, control the front view to steer. Let's look at the lane detection first. I created a file called lanefollowOpenCV.py, which includes a class lanefollowOpenCV. In stream.py, I'll import this library. Then I'll initiate an instance and keep it as the video camera class member. You can ignore the parameters for now. I'll talk about them later. In the getFrame function, we will call its followLane function. This way, the streaming code and lane detection code are very well separated. If later we would like to change to another method to detect lanes, it will be very easy to do so. Now we can set up the lanes. This is my setup. I use the blue painter's tape because it will not leave permanent sticky residue on the hardwood floor. I've used this frame as an example to show how lanes will be detected. Here we have the advantage that we know the color of the lane. So first we can isolate the color of the lane from the environment. This will reduce a lot of noise from later processing. If we don't do this, we will end up with this image as a result for edge detection. To isolate blue, we first convert the image from RGB color space to HSV color space. This is because in real-world images, there is always variations in the image color values due to lightning conditions, shadows, and even noise added by the camera. So different parts of the blue tape may show up as different values, some parts darker, while some other parts lighter. In HSV color space, the hue component will render the entire blue tape as one color regardless of the shading. The code to do this is the CVT color function. Note here that the conversion method is color BGR to HSV. This is because OpenCV reads image in BGR mode instead of RGB. Once the frame is in HSV color space, we can use the inRange function to filter out the color we need. The inRange function takes 3 parameters as input: the image and the lower and upper boundary of the needed color. By comparing the color of the tape in the HSV image and the color map, we can pick the lower and upper boundary. Here for hue, we choose from 80 to 170. For S and V, we choose a big range from 40 all the way to 255. After color filtering, we see a pretty clear lane, right? But it's for human. For computers, they are just a bunch of white and black pixels. Several steps are still needed for it to recognize them. The next step is edge detection. We use the canny edge detection function provided by OpenCV. The goal of edge detection is to detect pixels that are on edges. The canny function uses changes of pixels to do this. The code is pretty straightforward. The last 2 parameters are lower and upper threshold for how sharp the change should be to be considered a pixel at edge. If the change is above the max value, it will for sure be considered as an edge pixel. If below mean value, it will for sure not be considered as an edge pixel. If in between, it will be considered as an edge pixel if it's connected with other edge pixels. 100 and 200 are the commonly used values. If you would like to learn more about the candy edge detection, you can find the link to the OpenCV page in the video description. For lane following, we only care about the lanes that are close to the car, which is at the bottom of the image. We can further fill out the top part of the image to reduce potential noises. To do this, we create a mask for the bottom half of the image, then merge it with the edges image. The code is like this. First, we create another image with the same size as the original image with all the arrows. Then we specify a polygon whose vertices are 0 half has, Y's half has, Y's has, and 0 has. As you can see, this covers the bottom half of the image. Then we fill this polygon with 255. Now the mask image has all 0 for the upper half and all 255 for the bottom half. Using the bitwise AND option to combine it with the edges image will clear the upper half all out. Till now, these are still pixels. The next step is to convert these pixels into line segments. That is, for pixels that form a line, find the coordinates of the start and end point. OpenCV provides a function how lines P to do this. To put it simply, it tries to find lines that fit most pixels, as shown in the demo from OpenCV. This function has many parameters to control: distance precision, angle precision, at least how many pixels should vote for the line, minimum line length, and the max gap between two line segments to be considered as separate. This function returns a list of line segments, each represented by two coordinates for start and end point. You can see that the function works better for the left line, where two long lines were detected, while for the right line, many small line segments were returned. Here I draw line segments for the left line in green, while the right line in blue. But how can we know whether a line segment is for the left line or right line? Two observations can help us to do this. First, we notice that the left line usually has an upward slope, while the right one usually has a downward slope. Second, the left line should be located at the left side of the image, while the right line at the right side. We can use this to put them into two groups. Here is the code for the grouping. First, we create two lists to hold the line segments for the left line and the right line. Then we calculate the boundary of the left and the right region. Here I use the left half and the right half. You can choose a different value, for example, left 2/3 and right 2/3. Next, for each line, we get the two coordinates and use the polyfit function to convert them into slope and y-intercept, so we know the function of the line. If a line segment has a negative slope and the whole segment is in the left half, we consider it as part of the left line, similar for the right line. You may wonder that shouldn't the slope of the left line be positive while the right line be negative? Different from the coordinate system that we use in math, where the number on y-axis gets bigger while going up. For an image, the coordinate of the left top corner is 0, 0, where the left bottom corner is 0 has, which means the number for y gets bigger when going down. This is why the slope for the left line is negative and that for the right line is positive. Now we have many lines for either left or right. The next step is to get the average of slope and y-intercept for the two groups of line segments to get the slope and intercept for the two line lines. The average function calculates the average for slope and intercept stored in left and right. The makePoints function converts the average, the slope, and intercept to 2 points representing the start and end point, similar to the points we get from line segment detection. Let's use the left line as an example. We would like the line to start from the bottom of the image to the middle of the image. So y-coordinate of the first point is the image height, and y-coordinate of the second point is half of the height, which is the middle of the image. Since the line function is y equals slope times x plus intercept, then given y1 and y2, we can solve x1 and x2, which is y minus intercept divided by slope. We round it to nearest integer, since for an image, the coordinate needs to be a whole number of pixels. The next step is to calculate the angle that the front views need to turn based on the two lane lines. We first generate the line pointing to the direction that the car will go. Here is the code. The line starts from the bottom of the image, pointing to the middle of the image. Here we calculate the x and y offset from the midpoint of the bottom of the image. Y offset is always half of the hex, since it always points to the middle of the image. X offset is average of the x of the two endpoints minus the half of the width, which is the position of the midline. Then, with x offset and y offset, we know the tangent of this angle. We use the function a tan, which is the reverse operation of tangent, to get the angle in radian. Then convert it to degree. Since the front view's angle are already 90 degrees at ready state, we need to add 90 to the calculated angle to get the angle that we need to steer to. Sometimes there is only one detected lane in the frame. This usually happens when the lane turns sharply, for example this one. In this case, we can simply follow the direction of the single lane, so y offset will still be half of the hex, and x offset is x distance of the 2 points. There are several tips when writing the code for lane detection. First, to make it faster to test the code, you can add a main function to the line follow OpenCV.py. Then you can capture some images at different positions of your track to see how the code works for them. These are what I got from my track. If you do find issue with some images, you can use the second tip. You may have noticed that when constructing the line follow OpenCV class, the last parameter is called dry run. I use this to distinguish whether it's real self-driving or testing. If dry run is true, I'll store images for each intermediate step to check whether it works as intended. For example, this lines in detect edges function. Later I will show several examples how this can help identify the problem. Now after all the processing, we finally get the angle that the front views need to turn. We can get to the controlling part. We first add a button at the bottom of the control buttons to tell Packer to start following lanes. For stopping lane following, instead of adding a new button, I'll just reuse the previous control button, for example the forward one. Remember, when the mouse is up on the button, a stop action will be sent. The start lane following button will send a request with action equals to follow lane OpenCV. Thus, we need to add the corresponding processing code in the run function in views.py. Here we store the action in back view status. I also set the speed to 30 since I don't want the car to go too fast while following lanes. Turning the camera down by 20 degrees so it can better see the lanes in front of it. Note that if you do this here, when you take pictures to test the line follow OpenCV.py, you should do the same thing. As you can see here, we basically just store the back view status. We didn't do any control. The control happens in line follow OpenCV.py, where we detect the lane and calculate the turning angle. To do this, we need to pass the back view status and the front view instance to it, so it can know when to start control the front view, when to stop, and do the actual control. In views.py, I added several variables to store current status. I put back view status and speed in the status list to pass to the line following code. For now, we will only use back view status. Note that here we need to put the status in the list. This way, when the back view status changes in the run function, the line following code will know it. If you just pass the back view status, the line following code will make a copy of it, but will not know when it changes later. Then in the monitor function, we will pass the status list front view and back view instance to the video camera class. For now, we will only use status list and front view instance. Now you can see why, as a preparation, I moved the monitor function into the views.py. Accordingly, we need to add these parameters to the video camera classes in init function, which stores them as video camera classes members. Then in the getFrame function, after getting the image, we can check the status. If it's follow line OpenCV, we call the line follow OpenCV code and pass the front view and back view to it. Then in the follow line function, we can control the front view to turn. That's a lot of work, but now we can give it a try. As you can see, it works on some part of the track but fails on others. I added code to store images together with the angle while it's following the lane for debugging, then check the stored images to see why it fails on some of them. Here are two examples I found that the lane detection fails. You can ignore the red and blue lines in these images. They are there because I reprocessed the images which already have the lane lines and the direction lines from the previous results. In the first example, everything looks fine until the line segments detection. Although the edges look good, only a very small part of them are detected as lines. This may be because a lot of small line segments are detected which are smaller than the minimum line threshold. In the second example, the lightning is really weird while the car is moving, and even the color filtering didn't work. In the OpenCV processing code, there are many hand-picked parameters for color filtering, edge detection, line segment detection, etc. There are also lots of scenarios that are not processed in this code. For example, the moving camera case we have seen in the second example. We can add further logics to deal with the known issues, but it's impossible to hand-tune parameters and logics to deal with all complex situations in a real environment, especially those we don't know yet. So I will end this video here. You should have got an idea how we use image processing to perform lane following. In the next video, I'll show how to use deep learning to train a model which will be much more robust than hand-tuned logics.